Hello and welcome back to my CATIA V5 tutorial series. Today we will learn how to model a fully parametric spur gear that updates to the different inputs that you might have. A gear that looks kind of like this one, where you have all these parameters. We have the first three are going to be input parameters, and the other ones will just calculate the geometry of the tooth and the gear. So, for example, we have the module M. We can update this to whatever we want, update the part, and it will just calculate itself. We have like this is the pressure angle, we can update it, and we have the number of teeth. Switch it to 35, no problem. 50, no problem again. So you can pretty much change this to whatever you want, and it will still work, and it will respect the geometry. So if you have two gears like this, you can have one diameter on one, another diameter on the other one, and they will just mesh together perfectly. So to get started, we'll create a new part, and we'll start making our parameters here. Quick note, if you start adding parameters here and you don't see them show up here in your tree, that there's an easy way to fix this. First, you need to go to Options, under Infrastructure, Part Infrastructure, Display, and you need to click make sure these are checked, Parameters and Relations. Click OK, and they should start popping up here. So for the spur gear, first we had our input parameter, which was the module, parameter type of length. So this is M for the module, just so I don't have to reorder them. So this is the alpha type angle, and number of teeth is integer, which is the Z number of teeth. Right, these are the input parameters. Now we need the parameters that will get calculated. So we go to length. This is, most of them will be length parameters. New parameter of type. We'll call this A. This is the distance between the axis of the gear. We are just designing one gear, so we will not use this, but just put it here. So we have it in case we need it for later. We have the reference diameter, D. We will also put a parameter called R for the radius, because lots of formulas will use the radius rather than diameter. So this R corresponds to the diameter, the reference diameter. So this is like the reference radius. We will have the base diameter, dB. We have the base radius here. We have the addendum, which is called HA. We have the tooth depth, H. We have the tip diameter, which is called dA. Where we have diameter, we put RA as well, which is the radius. And we have the root diameter, which is called dF. And also we have the RF, which is the radius for that diameter. This will just be half this one, but it's much more cleaner to do it like this. Now we start adding formulas for it. The module, we'll just put it 2 for reference. The pressure angle is 20 is like a good value for it. Number of teeth, let's start with 20. And then you put the formulas here. Add formula for the distance between the axes. So this is like number of teeth Z1 plus Z2, but we'll just go 2 times Z2, considering we have like 2 of the same gear, because we're not going to use this now. This is just for reference to use later. Right, the diameter, add formula. Reference diameter is Z times the module, number of teeth times the module. The radius is half the diameter. This is the reference radius. This dB, which is base diameter, this is d times cosine alpha. Right, I tried it several times, but but it didn't like what I was doing. So when you get issues with parameters and formulas, it's easier if you just click on something rather than just typing it. Sometimes when you type it, it doesn't like it. The radius RB, this is just half of this one. The HA is equal to the module. You put M. The H, that formula, this is 2.25 times the module. The A, which is the tip diameter, is D plus 2 times the module. RA will obviously be dA time divided by 2. And the last one is the tooth, the root diameter. Add formula. This is D minus 2.5 times M. And this one will be dF divided by 2. Okay, now that we have our parameters set up, or most of our parameters set up, we should try to just create some circles to see where we are. So we will create our first circle. We put the radius here. So this is our, I believe it was our reference. The second one is our base. And third one here. So this is like the maximum where the teeth will be. This is the base of the tooth. And this one, which is the minimum one, this will be this will actually be the lowest point. So this is the base. This is where the profile starts being an involute. Okay, now how do we start drawing the involute curve? If you don't know, the involute is the curve described by a rolling circle without slipping. So a circle rolling without slipping will describe an involute curve. And luckily there is a formula for that. And that formula I will have somewhere around here is this one. It's defined through x and y, which is perfect for us because we will use them to define our points on this plane. Alright, so how do we do that? First, we will need to create a function. So a function, you go to this table here, and you have this law. Alright, click OK. Here you will need two parameters. One is h of type length, and the other one is going to be a real parameter, type real. Where is it? Real. There it is. Let's see t for theta. Based on the formula we just saw earlier, this is how we'll write it in CATIA. And we have this 1 rad to convert it to radians. Click apply. Okay. We call this h. Second law. We call this v. And we have our theta and length v. We click apply. And then we have our v function. Now we just need to put our points on this plane. So we need to link them to the laws. We go on the h, edit formula, put h, you need to delete the space that's already there and type evaluate 0. Yes, I wanted to update automatically. This one is actually v, and we have evaluate 0. And we click OK. And we have our first point. You can see it's on this circle, which starts from this point onwards. The profile of the tooth becomes an involute curve. Okay, we have this. We can, I don't know, we can copy it in a different geoset. Involute. Move it here. We need about 6 of these points, so we can just copy them. This one is the 0, 1, and this one you just change it here to 0.1, and you have to increment 0.1 for each of them, for each of the points. So this is 0.2, this is 0.2. You can see it's almost enough now. It starts to quickly run out of the maximum diameter, but we'll just make them here just in case. We might end up needing them afterwards. Okay, and the next one is 0.5, which is going to be really, really far away. Okay, now we take a spline and we connect the points in the order in which we created them. And we have one side of the tooth. Now we need to create the other side. What you need to do is copy them, and in this relation you type minus here. Oops. One thing to note about this this evaluate, it needs to be a capital E when you write evaluate. Otherwise it'll not work. It'll not recognize it as the function. So here we go again like this, minus, 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 minus. And we realized that what I did was actually wrong, because the V doesn't need to be minus, only the H. Okay, yeah, so I just realized that only the H needs to be a minus, a negative formula. The V stays positive, and you have this other involute curve here. Next thing you need to do is to rotate this curve to where it should be positioned here somewhere to create the other flank of the tooth. And in order to do that, there's a different formula. There's a lot of formulas in this video, unfortunately. There's a different formula to calculate the half tooth angle. It's called half tooth space angle. And we need to create it here. We need to go to parameters again, and we need to create this angle. It's a angle, new parameter of type, and we just call it F. It's F because I do not remember the name of the Greek letter that this is, and it kind of looks like a fork. No other reason. Edit formula. Here we have this formula. I've already written this in my notepad, and I'm just copy pasting it now. But this is basically the formula. Tangent of alpha minus alpha. Is this function here, and then make it okay. And there's an error. Normally, when you have errors, Normally, when you have errors in writing formulas, it's because it doesn't recognize the parameter. So what I had to do is delete the alpha here and write and double click this to get the connection to this parameter. Right, and this one we will have to then rotate. And the axis will be the x-axis and the value will be this parameter here. And it's the other way around, so it's minus f. It's minus 2 times f, of course, because this is called a half angle, and the full angle is 2 times. Now we need to create the tooth. Because of how wireframes work in CATIA, it is really advisable to have like a half circle instead of a circle when you do split operations. So we take the maximum and we take the minimum, we copy them and we put them here, and that means the formula will stay the same for the radius. And then we have this. Now what we need to do is to extrapolate this curve lower. We can hide this, we can hide the point as well, so we don't want to click the point. And then we extrapolate this like that. You can choose this as support, and here you can have like a length that you do, which is, I don't know, linked to the module somehow. Module 2 millimeters, that's kind of not enough, so 2 times the module, I don't know, something like that. We can have this like that as well. It's always good to have a support if you can, and we link it to the module like this. Now what we need to do is to create a radius here between this and this circle, and we do that by using the corner command like this. We make sure it's the right corner radius. This again can be like I think there are some design guidelines, 0.4 millimeters times the module, something like that. And here you can trim element 2, I guess. No, element 1. Yeah, that's the one. And you do the same here. This trim element 1, this should be 0.4 times the module. And you have this tooth here. Now what you need to do is cut it like that, cut it like that, and cut it like that. And you have your first tooth. All that's left to do is to pattern this around. Here you have complete crown, instances, you edit the formula, it's the number of teeth you want. Reference direction is X, and here it is. And then you join this to this one so you can have a single pad. Don't forget to uncheck connexity. And you have your teeth, and you have your base circle. What you have to do now is extrude them, or rather make a pad. Normally there's a little difference in thickness here, so I guess we need another circle which is connected to the base one. Which one is the base one? Let's see, this one. So we'll copy this. It's already linked to the, it already has the formula, this, but we need to make this slightly smaller. So how do we do that? We subtract. Let's begin with the module and see how it looks. It looks about right. That looks about just right. Okay, and normally there's another circle here, which is 7, I would say. Okay, now that we have all this, we switch to the part design. Go into our part, and we start making pads. First, we have the teeth. This will be, let's say, mirrored extent. This can be whatever you want. For me, because they're usually a function of the module, I can do this. This one will be also a function of the module, but actually this will be half the module. Why? You'll see that in a little bit. This one will also be mirrored extent module, because this is going to be slightly bigger. Now what I had to do before, which I didn't do, is go back into generative shape design, make this visible again, and I will join these two together without connexity. Go back to part design and make a path here as well. Module mirrored extent. And here I need to make a keyhole, but I just don't want to spend that much time now. And there you go. That's how you design a gear. You can update this to whatever you want. It will automatically update. You can hide this. You can change the number of teeth. You can change anything you want. It'll just work because it's properly calculated. See? It'll just update to whatever you input here. So that's a really good way to have everything parameterized, working nicely. You just need to design one gear for the rest of your life. If you want to 3D print or use some other cases, it's you just need to design one, and then the rest will just update these parameters in this one, and it's super easy to do. So that's been it for today. If you like this video, please leave a like and subscribe to my channel if you want to see more content like this. Have a nice day.